Hello, this is E637. I'm Charles Bouman, and today we're doing sRGB color spaces. So, let's see. I think when we last left off, our superhero was looking at the approximate sRGB transforms. So I'll pick up with that a little bit. So, let's see. Let me back up just a little bit, just to say sRGB is the standard color space that's used for most consumer, I should say, imaging applications. So if you get a file off your digital camera and it's pretty much in default mode, it's going to be an sRGB color space. So it's not perfect because the sRGB color space has some limitations, but at least everybody's speaking the same language. So that's a step in the right direction. And essentially what they did is codified what were some fairly widely used conventions. So first of all, they codified the use of the 709 color primaries, which are widely used in applications for video, for instance. Interestingly, the original NTSC color primaries were not 709 color primaries. They were less saturated. But the more modern standards use that, 709 color primaries. So basically, over here, RGB is the let me see, the tilde R, tilde G, tilde B are the I think those are the sRGB values. So and then the first thing you do is you have to linearize them. So they're gamma corrected, and to the first approximation, gamma correction is just a parallel kind of a relationship. So it's used so that well, of course we talked about gamma, so it's just like gamma correction for achromatic signals, only you do it individually to the RGB components. So you divide them by 255 and raise them to the 2.2, and 2.2 is kind of the agreed upon standard. Because if you raise, let's see, if you raise something to the, the physical devices that captured and displayed images tend to have a relationship which is about x to the 2.2. X to the 3 is probably more, better representation of the, a uniform color space for the human visual system, but particularly before, now this is my own personal interpretation, but before they had a lot of digital devices, implementing parallel relationships very precisely was tricky. If you're doing it with like analog devices, like you use diodes and so forth to try to approximate a parallel relationship, it's hard to do that extremely precisely, particularly as the power gets larger, because the derivative of the function is very large. If you're off a little bit, the function's approximation is quite poor. So I think that that was another reason people use 2.2 rather than 3. In any case, 2.2 is kind of the standard. Now, I should also mention, and I think it was said before, that this is not the exact sRGB relationship. I'm going to give you the exact in a moment, but it has various little things in it. So if you want to do it exactly, I'll talk about it in just a moment, but this is the concept, okay? So you first remove the gamma correction from each of the components, and you get linear RGB. So the RGB is linear with a white point of D65. So therefore, this is the colorimetric transform which you get that transforms you from a linear RGB space to XYZ, assuming that here XYZ equals 111 corresponds to equal energy white, and here 111 will, or 255, 255, 255 corresponds to D65. So, and I think in the earlier material, which Will must have covered some ground while I was gone. There was a calculation of how you calculated that matrix. So let me see if I can find it. Color primaries. Hold on. It should be in here. Oh, did I? Let's see. It should be one of these slides. Okay, NTSC. Just a minute. Hold on. Sorry. Here it is. So summary of approximate. Okay. So this is how you did the calculation of sRG, the transform from linear RGB in sRG color space to XYZ. So when I say sRG color space, I mean these are just linear RGB, which means they're linear in energy, and that there's RGB equal a constant has a chromaticity corresponding to D65, and that each individual R, G, and B component corresponds to the 709 color primaries. So from that you can calculate the matrix M that will get you from RGB to XYZ. So basically, and I talked about this last two lectures ago, that the idea is that if you can relate everything to XYZ, where XYZ is sort of a standard color space corresponding to where when XYZ equals 111, it's equal energy Y, right? Then you can get from any color space to any other, because you can always take it from sRG, from whatever color space you're in to XYZ, and then back to whatever color space you're going to, right? It's not always the most efficient thing, right? So if I wanted to drive to Indianapolis, one way of doing it is to first go to San Francisco and then go from San Francisco to Indianapolis, and you'd say, well, because I know how to get to Indianapolis from San Francisco because I've taken the red eye, okay? But yeah, you're reducing it to a solved problem, you know? But you know, from an engineering point of view, it might not be the most efficient thing to do, but that's good. But and then you can always take these transforms and merge them all together, and then do a single transform to get you from one color space to another. Okay. So now, what's I think important here is to understand, and there's a number of reasons why it's important to understand how to calculate this transformation matrix. And there's two important reasons that you want to know how to calculate this transformation matrix. One is because if you're actually manipulating color components, you'll need to be able to calculate these transforms from time to time so that you can get from one color space to the other. And the other is that because if you want to do well in the exam, you're going to have to know how to do this. Okay? Now the interesting thing is this. Okay, so let's see. Now, there's two constraints that we want to impose. One is that the one constraint is that the columns of M should correspond to the chromaticities of the R, G, and B color primaries. Okay. So if I look at this column. So this is the matrix whose columns are the. So basically, what happens is that you can think of it this way: is that M is equal to a matrix here, okay, and the matrices here are. This is the chromaticity of the R color primary, and then G, and then B color primary. Okay, and then over here there's a matrix which is going to be diagonal, and I'm calling it alpha 1, alpha 2, and alpha 3. Okay, and basically so what happens effectively is alpha 1 scales the first color primary, alpha 2 scales the second color primary, and alpha 3 scales the third, because any scale factor of these color primaries still represent legitimate color primaries. The problem is that when you mix them together in equal proportions, the color you're going to get out is different. Now, the color you get out when you mix these together in equal proportions is by definition the white point of the color space. Okay. So in other words, if you take M here and you multiply it by matrix 1, 1, 1, what you get out, or vector, what you get out is the color corresponding to the white point of that transform, all right? And this is getting back to my original point. This is distinct from two other. The white point, as I said, really has three different meanings. One is at least three different meanings in my view. Okay, one is that it tells you what color you get out when you put an input into the color space of 1, 1, 1. Okay, so it's just a property of the color space you're using. Okay, the other is that it's a way of describing. It's a way of managing, you might say, the color gamut of a device, okay? And the third is it's a cheap and dirty way, often, of handling color constancy issues in imaging systems, okay? But the only thing we're going to talk about here is the completely mathematical, quantitative, and deterministic issue associated with specifying a property of a color transformation. So when you put in 1, 1, 1 here, you get out a color, and that color you get out is called the white point of the color transformation. Okay, so when I change these values of alpha, I'm not changing the color primaries of the color system, because if I put R in, I still get the same chromaticity out. But I am changing the white point. So if I were to put in 1, 1, 1 here, then this vector multiplies. Then that would equal this. Then this vector multiplies that, and I get alpha 1, alpha 2, alpha 3, right? I multiply that, and that multiplies by this, okay? And that should be equal to the white point, okay? Now, there's actually two constraints. The white point is a chromaticity, right? So it specifies the chromaticity. It doesn't specify the brightness. So that really can be... so here what I do is I put little x, oops, I'm running out of space on this display. I put little x white point, and then I put little y white point, and I put little z white point. So those are the chromaticities. And that can be multiplied by any factor I want. But in practice what I do is I divide by little y white point, and I do that so that the transformation has the property that when I put 1, 1, 1 in, the y value that comes out is 1. It's just a matter of convention because I have to do something. Okay, so there's an unknown scale factor here. So basically, one way of looking at it is this. A matrix, a transformation matrix, M here is a 3 by 3 matrix, right? So how many unknowns are there in a 3 by 3 matrix? Okay, dun 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 dun. Okay, is anybody awake? How many unknowns are there in a 3 by 3 matrix? 9. Okay, because there are 9 numbers in here, right? Okay, now how many values are there specified by the chromaticities of three primaries? So, okay, there's 3 primaries, and how many values are there specified for each chromaticity?
3.
Chromaticity is specified by how many numbers? 2, okay? So there's 2 chromaticities, okay, times 3 primaries, right? So let me see if I can do this. Okay. Okay, now, so 3 times 2 is?
Wait, I know it's
6, okay? So right now, okay, so let's do this really quick. Okay, so there's 3 primaries. There's 2 degrees of freedom for chromaticity. Okay? So 2 times 3, that's 6, right? Now, in addition, but there's 9 parameters, right? So we're missing 3 degrees of freedom that we have to specify. So the white point has how many more parameters?
3.
Well, just the chromaticity of the white point.
2.
2, okay? So 2 for white point. So we have, that's plus, that's 8. So we're missing 1 degree of freedom, right? So the 1 degree of freedom we can set to anything we want. We could scale this to anything we want. So we could take m and we could scale it by any constant. But what will happen is that the chromaticity of the primaries will be correct, and the white point will be correct. But what will be wrong is that the overall, well, not wrong, but there's an overall scaling factor that we can set what we want. But a standard way of doing it is to make it so that when you put 1, 1, 1 in, the y value that comes out is 1. You could do it other ways too, okay? But, all right? So that gives you another set of equations. So that's this set of equations here. See, this is the chromaticity associated with the white point, D65. We divide it by 0.3290, which is here. So that's a 1 and 2 numbers, 1 on the top and the bottom, right? And then this is this matrix. The columns of this matrix are the chromaticities of the primaries, right? So the columns here sum to 1. Why?
Chromaticity is always sum to 1.
Because chromaticity is always sum to 1, right? That column sums to 1 also, right? Because it's also a chromaticity. And now we solve for these alphas by just using MATLAB. And the alphas come out to these values. We plug them in, and this is what the m we get, right? And the miraculous thing is I actually calculated this in MATLAB. And then I went to the website for sRGB. This is a number of years ago, so it may have been updated since then. And the numbers come out the same. Ooh. So, that's always amazing that you can actually reproduce those kinds of results, right? It gives you that warm feeling inside, like heartburn. And let's see. So anyway, that's this number. That's these numbers right here. Okay. So now what happens is that so now you take these linear RGB values and it gives you the x, y, z. Now from here you can go to anything you want. You can convert. You can compute LAB or anything else. Okay. Now it just so happens that and then the inverse transform is pretty much the same thing. Here it is. So you take m inverse of x, of the xyz, that gives you the linear RGB. And this is the actual inverse matrix, which has negative numbers in it. Right. So it's interesting to sort of reflect on this. So you can actually make, so can you make a sensor that has XYZ chromaticities? So in other words, can you make, let's say you put a CCD, right? This is a CCD. This would be a great test problem, by the way. I should write this down. I'll keep it. Okay, so this is a sensor, right? A pretty standard thing to do is what's called, to use a bare mask. So when you buy a digital camera, you might think that what they would do is they would have 3 sensors, one for red, one for green, and one for blue, right? But they don't because it's too expensive. So what they'll do is they'll have, say, green, because green is more important, and they'll have red and blue, and they'll repeat that. That's called a bare mask. Okay, and so forth. Okay, now what happens is this, that can you actually design a sensor here that has a green, so can you design the sensor so that it has a response as X, Y, and Z? Yes. Because I'm not sure you'd want to, but that's a separate engineering matter. But yes, you could, because you could design, theoretically, a physical filter that would have the response of the color matching of X, because X is strictly positive. They're all strictly positive. So in fact, they talk about it red, green, and blue, but they're really not red, green, and blue, because red, green, and blue are colors. The responses of these filters are not colors. These are functions that are applied to spectra. These are color matching functions. This is a massive point of confusion, incidentally. So it's not really R. Well, in practice, no one really ever designs X, Y, Z exactly either, because any kind of color matching function, I mean, there's a lot of practical considerations that come into the design of these filters, because the problem is you can either, you can't just, I mean, there's physical limitations of the material that you can use. So it's an engineering problem, okay? And I don't want to mislead you. Okay, so it's not as simple as anything I'm going to describe here. But if you had, and there's also issues of signal and noise in the CCD, so while you may have, some theoretical curves that you could have, in practice you may not want to use those theoretical curves because they would eliminate too much light, okay? So there's a lot of engineering trade-offs. But let's ignore all those. Let's say you have infinite signal and noise ratio in the CCDs, okay? Then you could make this... Y would be like G, okay? X is like red, and you would make that Z, okay? So you do X, Y, Z, and you can make those, in theory. It would be not impossible, because the X can actually have that response, okay? Now, and then your sensor would have an infinite gamut. There's no limitation in principle to the gamut of the sensor, because the sensor can measure X, Y, Z, and from those X, Y, Z, you can reconstruct any color. Okay? The problem comes out when you try to display it, or even when you store it. Now, the storage problem is an artificial one, but the point is this. So you could actually make this sensor so it would respond to X, Y, Z, and then you could put the X, Y, Z into this matrix, and you could get RGB out for the 709 primaries. And guess what? Okay, so you would have measured these X, Y, Z, and the X, Y, Z values you would measure would be positive, right? Because you can't measure a negative signal from a CCD. You'd have 3 positive values, but that's okay because these color matching functions are positive, and photons only are positive. You can't have negative photons. Well, I don't know. In physics, are they negative? I don't think they're negative. There aren't antiparticles to photons. I don't think, right? Okay. So anyway, so even if there are antiparticles to photons, we're not going to consider them here. Okay. So these are just positive. Okay. So you get positive value out here, and you put them into this matrix, but the entries in the matrix are negative. See, they're negative values, and they're not small, as a matter of fact. So the values of RGB you get out can be negative. And if they are negative, what does that mean?
It's just outside the gamut.
It's outside the gamut that you would have from a display device that used these RGB color primaries, right? So you have a choice. You could store those negative values in the format, or you can clip them off to be positive. In practice, mostly they get clipped off to be positive because standard color, image formats tend to only store positive values. Like if you use an unsigned character, then they have to be clipped. Okay. So then the format will limit the color gamut of the stored value. So in your camera, the camera sensor color gamut could be unlimited, but when it gets stored to the what is it called? The storage,
SD card.
Yeah, what is it called?
SD card.
SD card. When it gets stored to the SD card, then it gets converted to JPEG, say, and JPEG typically will use sRGB. It doesn't have to, but it typically will. And then this JPEG will only store positive values, and you'll clip, and then the gamut will be limited. Okay? All right. Are there any questions about that? So, okay. Now, another thing that's interesting that comes up, there's a very interesting problem. When you take the camera, then the problem is you need RGB values at every position. So you have to interpolate these. So that's called color demosaicing, right? And that's also an active area of research. Okay, so the exact XYZ to sRGB. Now, it turns out that for some historical reasons, the function of a gamma correction, even though all along I've been telling you that gamma correction was just a power law function, I lied, okay? Because it's not what they do, really. You know, I don't know. There may be some true believers, but my view is that they just, somehow or another, they got involved in some more complicated function, and now for legacy reasons, they have to support it. I'm not sure that there's any advantage to it myself. In fact, it's just kind of more complicated. But it is what it is, okay? And the difference is not insignificant. If you do the exact transform versus the approximate one, you will get different results that are visually distinct. So if you encode using one and decode the other, and then look at the two resulting images, the difference is significant visually. Okay, so so if you know that the system has been stored using the exact transforms, then you definitely have to implement them properly. It's not that much extra work once you've done it. It's just some extra software. But so these are the encoding, and basically what happens is that the idea is that rather it be a power law function for small x, they make it linear. And then they add a little bit stronger power to compensate for the fact that they use the linear value. And it all works out. It's supposed to, the function should be continuous at x. And in fact, I think the derivative is supposed to be continuous too, but I'd have to check that. But in any case, you can look these functions up. I think I double-checked this a couple times, and it's correct. But if you ever go to implement it, wouldn't hurt to look it up in another source, too. And the color transform matrix remains the same. This is designed so that when x is... hold on. So x is supposed to be in the range of 0 to 255. So when x is 255, then 255 in should equal 255 out. So it should come out exactly correct. And then the inverse relationship, this should be the exact inverse relationship to what I just showed you. So it's a little more trouble, but if you really are doing this, and if you work for a company like Thomson or Adobe, and they ask you to do sRGB, you should do it exactly correct, okay? But the other one embodies the conceptual idea, okay? Okay, now, this maybe part is becoming less relevant as the years go by, but it's still important, I think. There's still a lot of legacy that has to be supported in NTSC. In fact, even the HD color standards, I'm pretty sure, depend upon NTSC color transforms still. So you need to know them if you're going to work with, say, video. NTSC was the color standard that was originally encoded. I don't know. I'm not even sure what NTSC stands for, honestly, but it was put in place when TV first started coming out. Okay, so it really was a very successful standard. I mean, TVs today still take NTSC input, but it's not nearly as widely used as it used to. The NTSC input is the analog input with non-HD, where it's like what they call it's a coaxial 75 ohm plug, right? And I think it's sometimes called an RCA jack. So, and actually RCA, which is the Radio Corporation of America, was the company that basically created the NTSC standard, because that was where Sarnoff and Armstrong were. And there's today, this was all developed at Sarnoff Research Labs in Princeton, New Jersey. So, or a lot of that was done there. So anyway, those are like back from the 1940s, the late 1940s. So, so it's a very successful standard, but it's being supplanted now, obviously, by digital versions. There are a few things. First of all, the initial TV signal, analog encoding of the TV signal, and there's two. You have the video signal, okay, which is the baseband analog signal with the video on it that you would get on like I said, a coaxial RCA jack. I mean, it's the same. I mean, it's usually labeled just video, okay, on the back of like a DVD player or a TV set, okay. In addition, then you can take that signal and modulate it up on a carrier, and that's what gets transmitted at radio frequency, or RF, for terrestrial broadcast, right? So those are two different signals because one's modulated on the carrier. So for the terrestrial broadcast signal, you have to have a receiver that demodulates it down the video baseband, okay? But they're essentially the one's just a modulated version of the other, okay? So I won't go into it in a lot of detail, but they originally had the black and white standard. So black and white TV was out first. Achromatic TV was first, okay? And then later they added color to it. So they had to kind of make it backward compatible with the existing TV sets. So they injected the color in between. And that's like a miracle of signal processing. Basically what happens is that they have the TV set. So this was I just have to explain this because it's such a cool idea. Unfortunately, it doesn't really matter that much anymore. But the video the video signal scanned across the screen, right? And then there were basically 480 lines approximately. It might have been, I don't know the exact number, but I think it was 483. But the last three lines weren't displayed. They were used for the flyback because when you get down to the end, it has to go back to the beginning. So you need some extra time in there, and so it would scan across, and then there's a certain amount of waiting time. See, the analog signal had to be designed so it could actually work with real analog electronics. It wasn't like today where you just encode everything as compactly as possible. You send it over to the computer and it decodes it, okay? There was no storage. So as the video signal's going across the screen, okay, it writes on the screen, and then there has to be a blanking time that gives time for the electron beam to come back again, and then it writes across, okay? So now what will happen is it writes first the even lines, and then it writes the odd lines. That's the interlaced video. But now what happened is they had to inject the color. So what happens is that adjacent lines in the screen are pretty similar. So it's almost periodic. So since it's almost periodic, if you look at it in the frequency domain, you get a comb structure. Because the spacing between the kinds of cone is equal to 1 over the period of the time it takes to trace across the screen and come back again. Okay, because that's essentially the repetition rate. So they injected the color in here. They injected the YIQ, but even then they had to be very careful to try to put the color signal. They only want to encode exactly what's necessary because they had to inject it in here. And it used to be if you got a fancy analog TV set, it would have a comb filter in it. The comb filter would do a better job of separating the color and the black and white out. But what would really happen is that that if there was a lot of high-frequency content in the vertical direction here, then it would screw up this comb structure, and some of the gray achromatic signal would get into with the color. And then you'd have crosstalk between the color and the black and white. And what would typically happen is if you had a lot of high-frequency content here, you would get like rainbow effects because the monochrome, the Y channel, the achromatic channel would bleed into the channel, and you'd get artifacts. So later, then initially they just had video, and that was used for a long time. Okay, and then later there was component video. Actually, at one point there was also a thing called S-video. So S-video and component video were different mechanisms for just separating out the color channels. So later on, rather than actually adding these two signals together, excuse me, they actually kept them separate so that you wouldn't have this crosstalk, and that would allow you to have higher frequencies in the vertical direction. But fundamentally, and by the way, that's why you have 480i, okay? 480i and 480p, which are, if you've gone to buy a television set, they talk about that. Because 480i would basically be the old standard, okay? So the idea is there you have 480 lines down, and they're interlaced, so which means that every line is only updated once every 30th of a second. If it's 480p, then every line is updated every 60th of a second. So the component video avoids this problem. Yeah, now, of course, it's all encoded digitally for the HD. And the HD supports different modes, 480p. And, of course, everybody wants 1080, 1080p, right? Which is, means that you have 1,080 lines vertically. Now, it used to be when they marketed these TVs, they'd say there were 720 lines. That was some equivalent measure of the frequency response of the video along the horizontal direction. But the number of lines in the old analog standard is fixed. You can't increase the resolution fundamentally along the vertical direction. It's not. You can only increase it. You can increase the bandwidth of the signal in this direction. So the point is, you're going to have the so-called black and white, and the chrominance components. So there's three components, right? There's sort of you have red, green, blue, right? But we're going to transform that to another system which has like the brightness, the achromatic component, and then the two chromaticities that you add to that to essentially colorize the image. This is the way the analog standard incorporated color, because they had to be backward compatible. So what they did is that the Y component when we did X, Y, Z, the Y component is formed by the following combination of red, green, and blue. Okay, you can just read this off the matrix. We did the calculation, but that's true when you use a C white point and NTSC color primaries. And the NTSC color primaries were substantially less saturated than the 709 primaries. Okay. So if you go back there, amazingly enough, when you do the calculations, you actually get the same numbers. And these are the standard numbers for computing Y from RGB. But then, being engineers, they said, okay, fine, but we don't really want to compute linear RGB. You never really want to be dealing with linear RGB because it's very prone to distortion because it's in the wrong coordinate systems. By wrong, I mean it's not coordinate systems which are uniform, where distortion is uniform, with the human visual sensitivity, all right? So what they did is they said, well, we'll just use the gamma-corrected RGB in place of the linear. So this is a very strange transform. This is not Y. It's just Y computed from the gamma-corrected values, where you use the same values of the weights you would if it were the linear RGB with NTSC color primaries and C white point. So this is still how you compute Y, okay? Even though the color primaries are no longer NTSC, it's not a C white point, and they're not linear. Okay? So it's just a historical thing, right? I mean, so the transform is all wrong, okay? But it's what they do. So if you want to decode a digital signal today from a TV set, the Y component is formed by this, where R, G, and B here are the gamma-corrected RGB color RGB values using whatever color system you're using. So in particular, usually these will be gamma-corrected with 709 primaries. But the weights result from the assumption of other primaries. Okay? It's just the way it is. Okay? So this is how you compute. So from the other point of view, if you have a digital camera and you want to encode digital video, the first thing you do is you measure. You have the sensor and you convert to sRGB color coordinate systems, right? So the R to G to B will be like sRGB, gamma-corrected sRGB. Then you add them together with these weights to get the Y component. Okay? Then what you do is, then there's a thing called there's a thing called YPBPR. Now, if you look on the back of a DVD player, it still, I think, has YPBPR on it. YPBPR are they're just formed by taking now the beat. Again, these are gamma-corrected RGB in whatever color space you're using. Usually it's sRGB. and then you take B minus Y and R minus Y, and that becomes YPBPR. Then from YPBPR, if you divide them by these magic numbers, you get YUV, okay? And now, if you do a rotation by 33 degrees in this coordinate space, you get YIQ, okay? This is just standards. You might say, well, why did they do this? I mean, like, I can try to explain it, but it really doesn't matter. This is just what it is, okay? You know, there was some logic behind it all in that and actually, you know, the standard was amazingly successful in that they found that they could get, if they transformed to this YIQ coordinate space, they get the least sensitivity to distortion in the human visual system, and the Q is the less important. Q is basically like the opponent color space and blue-yellow opponent color space. And I is like the red-green opponent color space. And this is the actual transform. Now, what will end up happening is very often you'll get data. So you might get like HDTV data, digitally encoded data, right? And people will say, oh, it's in YUV color space. How many people have ever gotten video data and someone told them it was YUV color space? Oh, it must have happened to somebody. Okay, at least one person, thank you. Okay, I'm sure it's going to happen to other people. Because when that's very common. In the digital video community, people will send data to each other and they'll say, this is YUV, okay? YUV doesn't mean YUV, okay? YUV isn't a digital standard. It's an analog standard. YUV is basically an intermediate format that takes you to YIQ. YIQ is what's actually encoded when you have the injected color space in the video. So if you have when you actually have an NTSC video, then it's using YIQ, okay? YPBPR is what they use for component video. Okay, so it's a small modification, right? They just eliminated this extra transform, I guess, because they felt like they really don't need it. The advantage of the transform is that you can have some additional distortion, and it's not so egregious. So here you have separate cables. There's no significant loss, so it's not a big deal. So when people talk about YUV with digital data, what they really mean is that they're using what's called YCRCB, okay? So YCRCB has the same color coordinates as YUV, because you see here for YCBCR, you take B minus Y and R minus Y, which is exactly what you do here. But the scaling factors are different, and there's an offset of 128, so that these values will come out in the range 0 to 255. Because if it's digital data and it's 8-bit precision, so it's unsigned characters, then it can't be YUV, because YUV is a analog representation. So when people say YUV, they mean YCRCB. And this is the way data is encoded for modern digital video. So HDTV. As far as I know, it's also used for encoding of DVDs on movies, but I'm not absolutely certain of that. But certainly for any HDTV terrestrial broadcast television, this is how it's done, as far as I know, unless there's something about the standard I'm aware. But okay, so that's pretty much it. So the main upshot here is just, I know, one other thing, just to review a few points. Okay, so technically YPBPR, YUV, and YIQ all assume NTSC primaries with C white point, except for nobody uses them that way anymore, okay? So same transformations may be used with other white point and color primaries, and inevitably they always are. Today they're always used, they're by far and away the most common usage of these color coordinate systems are with the 709 primaries and the D65 white point. So 709 primaries and D65. High definition and standard definition TV use 709 and D65 color primaries. All transforms are performed on gamma-corrected RGB data, where the gamma correction uses the exact formulas for sRGB gamma correction that I gave you. Okay. The nominal bandwidth. Okay, so YIQ is specifically designed for modulation on a carrier. So there, the bandwidth is important because if you have too much bandwidth here, what will happen is that you have interference then because the color injection won't fit in between the values here. So the standard said that I was supposed to be limited to 4.2 megahertz, y was 4.2 megahertz, I was 1.5, and Q was 0.6. And those megahertz numbers actually have some meaning because basically, if you know you're updating this frame, if you know you're drawing 483 lines every 1/30th of a second, and then modulo a few little details having to do with the blanking time. Okay, basically that specifies how fast you draw across this line. So knowing the bandwidth of the amplifier tells you the spatial bandwidth in terms of cycles per line. Okay. And if you take the cycles per line and, I don't know, divide by 2 or something like that, okay, multiply by 2, I'd have to think about it a little bit. You can get the equivalent Nyquist rate. So that basically specifies the equivalent number of samples on a line, okay? So these megahertz numbers have an absolute meaning is what I'm saying, okay? Megahertz equates directly to samples per line in terms of resolution. And in the old days, the people who were really into video, they had an intuitive feel of that relationship, and I don't, okay, because I didn't deal with it that much. And the chromaticity coordinate system is approximately an opponent color system. So we'll see that I is effectively something close to blue-yellow, and Q is something close to red-green, okay? 29, okay. Any questions then? Here are some interesting slides that I included, and I think this question came up before. If not, I think I brought it up, which is that, is the color sensitivity in all these regions of the color space the same? And the answer is no. This is a mathematical transform, which is very useful, but perceptually it's not very precise, okay? So you're very sensitive in some places and completely insensitive in others. So that's a little bit of a problem. These are called McAdams ellipses, and they're 10. So I think it says here they're 10 times enlarged. So what happens is you take a person, you have them do a color matching experiment. When they do the matching, they're going to be off a little bit, right? So you keep track of how much they're off, and you look at the uncertainty of the match, and then you can do a covariance estimate. And since you guys did that eigenimage decomposition thing, okay, you know all about this, that there's going to be two principal axes, and then the square root of the associated eigenvalue tells you the standard deviation along that axis, right? Or the reciprocal of the standard deviation, okay? And then, depending upon how you look at it. And then, so that's what these ellipses represent. So here the uncertainty of the match is large, so that you need to change a lot in order to be able to see any difference. And here the uncertainty of the match is quite small. So that means that, what does this tell you? It tells you that chromaticity coordinates, little x, little y, are not going to be a good coordinate system to do quantization in. So if you have chromaticity coordinates, what do you want to never do?
Encode.
Excuse me?
Encode them.
In what format would be bad? In using what kind of discrete, like on a computer, what variable type would you not want to use? Integer or unsigned character. What variable type would you want to use?
Floating.
A float or double, right? So the moral of the story is this: never represent linear quantities with integer values. Always use floats. If you're going to use an integer value, it has to be gamma corrected. Okay? That's the first rule of image processing. All right, thanks. Bye.